Dear students, welcome to this session of the lecture on gas turbines. Today we will discuss on an illustrative example related to gas turbine. This problem is taken from one of the examination in the semester conducted by MacOut in 2017-18. The paper on thermal power engineering. Now the problem statement is uh, a gas turbine unit has a pressure ratio of 6:1 and a maximum cycle temperature of 610 degrees centigrade. The isentropic efficiencies of the compressor and the turbine are zero point 0.8 and zero point 0.82 respectively. Calculate the power output of the plant when air enters the compressor at 15 degrees centigrade and 1 bar at the rate of 16 kg per second. Also calculate the thermal efficiency and the work rate of the plant. The given property values, that is Cp here, that will be Cp. Cp is equal to 1.11 kg per kilojoule per kg Kelvin for combustion. That means here in this problem, for different processes, the specific heat for constant pressure are differently taken. That means here the combustion, compression, etc. are having different, for example, the combustion, after combustion and before combustion, the gases are different. So that is why these are taken differently. So before compression, it is air, that is Cp is equal to 1.005 kilojoule per kg Kelvin and gamma is equal to 1.4. This is for air. And after compression, that is during combustion and during the expansion process in the turbine, the Cp values are taken for the product of combustion, that is 1.11 kilojoule per kg Kelvin during combustion and 1.11 kilojoule per kg Kelvin during expansion in the turbine. So during turbine also it is actually product of combustion, that we have to keep in mind. And this Cp, the second one, Cp is equal to 1.005 kilojoule per kg Kelvin and gamma is equal to 1.4 for compression. This is for air. Okay, now this is taken from one semester examination question paper. Now we will try to solve this problem. The problem statement rewritten here. The known quantities are shown with green color and the quantities to be determined are shown with red color. Now we will see the cycle diagram for the gas turbine. Here we are considering the ideal cycle, that is air standard cycle for the gas turbine, that is the Brayton cycle. We are considering the thermodynamic diagram, two thermodynamic commonly used diagrams, that is PV and TS diagram. Here, PV diagram, the first one, the PV diagram, and the second one is the TS diagram. Now, as we know that the Brayton cycle has four processes. The first is 1 to 2 is, that is ideal cycle. Here I am showing the ideal cycle. Later during solving the problem, we will try to see what are the actual processes. Here we are trying to see the ideal processes. 1 to 2 is the 1 to 2 is the isentropic compression. 2 to 3 is constant pressure heat addition. 3 to 4 is isentropic expansion, and 4 to 1 is constant pressure heat rejection. So these are the four processes. Now the same processes are shown in the TS diagram also. 1 to 2 is isentropic process, constant entropy that you can see, that is a vertical line. Then 2 to 3 is a constant pressure process, that is isobaric heat addition. Then 3 to 4 is again isentropic expansion, and 4 to 1 is isobaric heat rejection. So that these are the processes. Here you can mention, here you can write that it is entropy is equal to constant this process, and entropy is equal to constant this process. And here it is pressure is equal to constant this process, and pressure is equal to constant this process. I am not showing here these two because this is horizontal line that you can quite clearly understand that this is a constant pressure process. So I did not mention it here. Similarly, this one also constant pressure process, and this is constant entropy process, and this is also constant entropy process, as this is the entropy axis. Okay, now these are the two things that uh, is required to understand the problem. Okay, next we will write therefore the given data. We will first write the given data. Given now, given is that pressure ratio is 6:1. Pressure ratio means you want to understand one thing, that here I have drawn the cycle diagram in such a way that it is P1 and it is P2. So pressure ratio can be clearly understood. So there is a ratio, there is a pressure rise in the compression, and there is an expansion, that is fall of pressure during expansion in the turbine. So this is P2 and this is P1. So pressure ratio means basically the pressure ratio between the compressor exit and the compressor inlet. As we know that compressors are used to increase pressure. So here given data, therefore we can write this is P2 by P1 is equal to, all the steps you have to clearly understand. P2 by P1 is equal to 6. So that is written as RP for the Brayton cycle, that is pressure ratio. Okay. Now, another thing is given here, you see that the maximum cycle temperature is given as 610 degrees centigrade. That we have to understand clearly, that maximum cycle temperature when it is reached at point 1, this is the inlet to the compressor. So in a gas turbine, that is the starting condition, that is the means initial condition. So 1 to 2, during due to compression, there is work transferred to the gas, so temperature increases, that we can see here. 1 to 2 temperature increases, and 2 to 3 also there is a temperature increase because there is a combustion, so there is heat addition, so temperature increases. Now 3 is the point where the temperature is maximum, because here we are supplying work to the gas, that means adding energy in terms of work, and then from 2 to 3 we are adding heat, that is the energy in terms of heat. So in both these two processes we are adding for supplying energy, and therefore the temperature increases. So 1 to 2 L and 2 to 3, in both these processes temperature increase, and at 3 the temperature is maximum. So maximum temperature 610 degrees centigrade will be at point 3. That we have to understand. That sometimes student mechanically remember or memorize, but that is the explanation, that when the work is applied and after that heat is applied, so after supplying both these energy, then the temperature becomes maximum. After that, the energy that is supplied, now the gas will basically spend that energy to do the work, and after that it will again cool, it will be cooled, and some heat will be extracted or heat will be released by the gas, and the temperature will come back to 1. That is a closed cycle gas turbine. So it is 1 at is the initial as well as the final state. Okay. Now, therefore, here it is a maximum temperature 610 degrees centigrade, and the initial temperature also given here, that is the compressor inlet is at 15 degrees centigrade and 1 bar. So this is one that is shown, that initial temperature 15 degrees centigrade, and this is 610 degrees centigrade maximum cycle temperature. These are the two things we have to clearly understand. And P1 is equal to basically 1 bar. So that is 1 bar. So P1 is equal to 1 bar. Okay. Next, what is known? Mass flow rate is given as 16 kg per second. Now, one thing that I would like you to follow or note here, that before this 16 kg per second, nothing was mentioned in terms of the extensive properties. In thermodynamics, you have studied intensive properties and extensive properties. Intensive properties means it is independent of mass, and extensive property means that depends on mass. So this is the mass flow rate, that is the only extensive property here it is given. Now, depending or using this property, we will be able to calculate all the properties that are related to mass, like say total power. Okay, so these are the quantities that are related to the mass, total property. If this mass flow rate is not given, then we will be only able to calculate the quantities per unit mass. So that you have to check whether in a problem, if the mass flow rate or such extensive properties like total heat transfer, etc., are not given, then you will not be able to calculate the extensive properties in that problem. That you have to follow. So while reading out the problem statement first before solving the problem, then you must note that whether the extensive properties are given or not. All other properties are intensive properties that you can see. 610 degrees centigrade, 610, 15 degree, 1 bar, all these are basically, or 6:1, all these are basically related to intensive property. So this is the first quantity related to extensive property. So mass flow rate is given. Now we will simply note that, therefore, maximum cycle temperature is 610 degrees centigrade, and we have to convert this to Kelvin, because we will be using this in the equation of state and related things. So we have to use the absolute temperature. So it is 610 plus 273.15 Kelvin. So that is 883.15 Kelvin. Okay. Now, another thing that is given here, is T1, that is the initial temperature. Initial temperature T1 is equal to 15 degrees centigrade is equal to 15 plus 273.15 Kelvin, that is 288.15 Kelvin. Okay. Okay. Now, here we see that two quantities are given, that is isentropic efficiencies of the compressor and the turbine. Now, what is isentropic efficiency? That let us see. Although during solving the problem, you don't have to explain many things. You just use the formula or equation and then solve it. But for your understanding, I am showing it here. I will show the isentropic efficiency in the TS diagram. So I will show the constant pressure lines because there is a change of pressure during the compression. So when compression is taking place, so this is P1 and it is P2. So when the compression is taking place, you see this is the compression. So 1 to 2 is the compression process. Now isentropic efficiency is related to this process. Now let us see what is the meaning of that. Now during this process, basically, so this is the isentropic process between 1 and 2. So it is 2. Now, if it is isentropic, I can write it as 2s because S means entropy. So it means that following constant entropy, the compression is done from 1 to 2. Now, here it is given that isentropic efficiency is 0.8 for the compression. So that means that there is a deviation. So if it is 100%, then it would be following this line 1 to 2. Otherwise, if there is a change, that means if it is not 100%, then there is a deviation from this process. So deviation means basically there will be increase in entropy. Okay, increase in entropy during the compression. So there will be basically so it is like this. So now we will write here 2A means actual process. So what is the meaning of isentropic efficiency? That here during process 1 to 2, there is some enthalpy change. So basically, when the work done is calculated, we basically calculate the change in enthalpy. So during this process, the work done or work required for the compression is H2 minus H1. That is H2S minus H2, H2S minus H1. Now, during the actual process, it is more that you can see. So here, due to the deviation, means what happens basically Isentropic, if it is not isentropic, that means basically it is, what is the meaning of isentropic process? In thermodynamics, isentropic is basically a combination of reversible and adiabatic process. So isentropic means basically reversible and adiabatic process. So isentropic means basically reversible and adiabatic. Now here that we have to understand one thing, there should not be any misconception. So if the process is reversible and adiabatic, then it is isentropic. That is the reverse thing. Means if it is reversible and adiabatic, then it is basically isentropic. So isentropic does not mean that it is reversible, or isentropic does not mean it is adiabatic. So if it is isentropic and reversible, that means it will be also adiabatic. Or if it is isentropic and adiabatic, that must be reversible. So that should be understood. One thing. Another thing is that here, during the actual process from 1 to 2, there will be basically non-isentropic, means entropy changes due to friction. Okay, the process remains adiabatic. There will not be any heat loss, but there will be irreversibility due to friction. So frictional loss will be there. Loss will be there, frictional losses will be there, and that will make the process irreversible. Frictional losses make the process means compression process irreversible. That we have to clearly understand. That means during this process, there is no heat loss, but there is frictional loss. So mechanical loss, that means some resistance to work will be there, and therefore there will be some loss. And therefore, the work required for compression will be more compared to the theoretical one. So this is the theoretical process. During this process, the work required will be something, and during the actual process, due to frictional losses, the work required for compression will be more. So isentropic efficiency is defined as isentropic efficiency for the compressor. Remember that these you don't have to write whole explanations during the examination. You don't have to write. Only thing, this is for your understanding. So let me write those things with orange color that you okay, sorry. So isentropic efficiency of compressor we will give the symbol as eta C S. C means compressor, S means entropy. Eta is the symbol for efficiency. So this is basically W C S divided by W C actual. WC means work for compression during isentropic process divided by work for compression during the actual process. So you see that it is the theoretical process, it requires it requires less work compared to the actual one. So that is why the less one is written in the numerator, and the more one or greater one is written in the denominator. Okay, that will change for turbine. Okay, that we will see. Only thing that you have to keep in mind, that since it is efficiency, and efficiency is the ratio of the the less divided by the more kind of thing. Okay, so it is the compressor work input for isentropic process. Compressor work input for isentropic process divided by the compressor work input for actual compression process. Okay. Now, what is that? Therefore, during the isentropic compression process, it is mass flow rate multiplied by the change in enthalpy. So that is equal to mass flow rate multiplied by mass flow rate is 16 kg as given. So it is 16 kg per second. Mass flow rate multiplied by change in enthalpy. Change in enthalpy magnitude, if we write, then it is H2S minus H1 divided by H2S divided by H1 divided by H2A minus H1. So it is mass flow rate H2A minus H1. So after cancelling the mass flow rate, so it will be a eta Cs is equal to H2S minus H1 divided by H2A minus H1. So that is one thing that we will need to use. Now here for the turbine, we will see again the same thing. Now during the turbine process, same thing will happen. You see the processes are same. Sorry, the pressures will be same. P1 and P2. Here you can see that P1 is same as P4 and P2 is same as P3. So this P2 is same as P3 and P1 is same as P4. So we will write the same pressures. Now we will show this process 3 to 4. Here the ideal process is isentropic 3 to 4. Now here it is mentioned that there is an isentropic efficiency of the turbine which is not 1, which is less than 1. So there will be again deviation from the ideal process that we will see now. So this 3 to 4, there will be a deviation. Now we will draw the same pressure line here again, or we could draw it here also. Now let us show it here separately. So there will be pressure line. Now we will draw the isentropic process, that is 3 to 4. 3 to 4. This is 3. Now 4, this is 4. So we will write this as 4s because this is the fourth state following the entropy constant line. Now, since there will be entropy, that is irreversible process, there will be entropy change. Now, entropy change, you see that irreversible process means entropy will change. Now, always we are showing that entropy is increasing. Why? Can you answer? We are always showing that entropy is increasing. Entropy could decrease also. Okay. Entropy could decrease also. But here we have to understand one thing, that the processes are adiabatic. So there is no heat loss. So during the friction, there will be basically heat generation due to the frictional rubbing. There will be basically entropy increase. So that heat loss is not there, and entropy change is always increasing in the system. So that is why it is increasing. Otherwise, if there would have been some heat loss due to heat transfer, then we could not conclude that whether the entropy will increase or decrease. Okay, in that case, that would have been inconclusive, that whether entropy will increase or decrease. But here, since the process is adiabatic, and since it is adiabatic, there is no loss of heat, and due to the irreversibility, the entropy always increases. Therefore, there is no entropy decrease due to heat loss, and there is always entropy increase due to irreversibility. That is why the entropy increases always. Okay, that you have to keep in mind. Okay, now here the same theory we can write, that isentropic efficiency of the turbine, if we try to write. So isentropic efficiency of the turbine is equal to, as similar to the compressor, follow the notation. This is W. Now you see that there is a difference. There is a change. For compressor, the actual work required is more compared to the ideal work input. So the actual work input is more compared to ideal work input. But for turbine, the actual work output is less than the ideal work output. So here the isentropic efficiency is defined in the reverse way. That is, it is actual work output during the actual process divided by the work output during the, or enthalpy change during the isentropic process. So this is basically W. It is defined as the turbine work output in actual process divided by turbine work output in the isentropic process. Actual process means actual expansion process. Turbine actual expansion process. Turbine work output in the isentropic expansion process. So here it is basically W T actual divided by W T isentropic. It is just reverse of this. In that case, it was the isentropic was in the numerator and actual was more than that. So it was in the denominator to make the efficiency within one. That means within 0 and 1. Here, the actual work output is less compared to the isentropic. So it is the ratio of actual divided by the isentropic to make it within 0 and 1. Okay. Next, it is therefore in the same way we can write in terms of enthalpy. It is the enthalpy drop during the actual process. So what is that? H3 minus H4A. H3 minus H4A. Cancelling the mass already mass flow rate. So it is H3 minus H4A divided by H3 minus H4S. Okay, one thing. Another thing is that we have to keep in mind that these are basically ideal gas. Okay, so therefore, we can write the enthalpy change in terms of the temperature change. So what is that? We can, because we will use that. So let us write it here. So what is delta H? Delta H is equal to Cp dt. So it is Cp during the compression. So since Cp values are different, so Cp during compression we may write. What is that? Therefore H T2S, that is delta T. Here it will be delta T. So T2S minus T1. This change in temperature multiplied by the specific heat. Now, therefore, it will be Cp C T2A minus T1. Therefore, cancelling that Cp, you can write it is T2S minus T1 divided by T2A minus T1. In the same way, we can write this also as, now here the Cp value will be different definitely, but it is same for the isentropic as well as the actual process. So they will cancel in the numerator and in the denominator. So it will be basically T3 minus T4A divided by T3 minus T4S. Okay, we can put some equation number to this. So let us name them this as equation 1. This we may write as equation 1. This we may write as equation 2, and this we may write as equation 3. Okay. Now, what is given, that here given data, moreover given data are basically compressor isentropic efficiency is 0.80 and turbine isentropic efficiency is 0.82. Also, another thing that is given is P1 is equal to 1 bar. Here, another thing is given, P1 is equal to 1 bar. Okay. Next, what is to be determined? To be determined are power output of the plant, what is that? Basically, W dot net. Net power out. Net means basically, finally, the turbine work output will be positive and compressor work input will be negative. So subtracting the compressor work input from the turbine work output, we will get the net work output. So that this power output is related to the subtraction of the compressor work output from the turbine work output and taking in proper rate, that is per unit time. Now thermal efficiency next to be determined. First to be determined, second is the thermal efficiency. Of the plant is equal to thermal efficiency. Eta thermal is equal to what? W net by Q net, Q in. Or W dot net by Q dot in. Both are same. Third one to be determined is the work ratio. Now, work ratio of the plant, it means that it is the net work output divided by the turbine work output. So this is W net divided by WT. W net means what? W net means basically WT minus WC. It is the net that is turbine work output minus the compressor work input, and this is WT. So it is basically 1 minus WC by WT. Okay. So this is the definition of work ratio. There is another quantity called back work ratio that is generally uh, another quantity that is defined. In that case, that is basically the compressor work out input divided by the turbine work output, back work ratio. Okay. Now we will go for solution. Follow the solution strategy carefully. Now see that so far we have discussed many things. You will use only the formulas, means basically the final expression you will use during the examination. You need not derive all these quantities separately. If you write, means simply this one and simply from that this one, that is okay. Okay, just writing that, it will be okay. Many elaborate discussions or explanations or definitions are not required, because the problem has say only 7 or 8 marks, so you need not write many things for 7 or 8 marks. Okay, because it will take a lot of time. So this was discussed just for your understanding. Okay. So now we will write the use the quantities that are mentioned or given, and we will try to solve the problem. Now for ideal turbine, it is now we will write the first law. So we can write the first law. Now, first let us draw the actual cycle diagram, because as we know that these processes are deviated from the isentropic process. So there will be a deviation in the cycle also. So let us draw the actual cycle diagram, and then we will solve the problem accordingly. Now in the PV diagram, it will be basically First, let us draw the TS diagram. Let us first draw the TS diagram. As we know that there are deviations, so we will show the deviation and then we will confirm the process, and finally we will draw the tick lines. So we will simply draw like this. That means this will be the actual process now, 1 to 2A. This is the ideal process and the actual process is this. So it is 2A and is 2S. Now again from 3 to 4, there will be one isentropic process and there will be one actual process. So this is 4A and this is 4S. So if we draw with some other color for the process, the cycle, so it will be like so this will be the actual cycle. Now we can draw the same in the PV diagram. So 1 to 2. You see that this is basically P and this is 1. So here it will be 1 here as earlier 1. 1 is the initial condition, that is unchanged, so 1. And then 2, where it will be 2a. 2a, it will be seen that 2a is in between 2s and 3. So earlier 2 2s was here, so 2a will be in between, somewhere in between 2 and 3. So it is between 2 and 3, as it is seen that here it is between 2 and 3. So 2a will be in between that. So let us draw that. So this is 2s. So 2a will be in between somewhere here. So somewhere here. So it will be here. Remember that all these things I am drawing for your clarification. Many things you don't have to draw during the examination. Okay. So where is 4a? 4a is basically somewhere after the 4s. You see, as you see here. As you see here. So 4a is out of, means it is outside 4, 1 and 4. So outside 1 and 4. You see, it is outside 1 and 4. So it is beyond this point. So it will be somewhere outside. So if it is 3, if it is 3, then 3 to 4 will be somewhere here. Three to four will be somewhere here. And therefore 4 will be here, as 4a is here. So it is 4a. It is 2a. Therefore, this is the side. Okay. Now let us write the quantities. Now here we see that in these terms, all these are basically W in terms of either work or heat. So let us write these quantities first, and then we will see what should be the strategy for solving the problem. So first we write W dot T S, that is isentropic work from the turbine, that is equal to m dot into delta H across the turbine. What is that? 324. So it is m dot to Cp for turbine multiplied by delta T. So that is equal to m dot Cp for the turbine multiplied by T3 minus T4s. T3 minus T4s. Actually, this is theoretical. This is theoretical. Again, for the actual one, what is that? WT actual. WT actual, that is this one. WT actual is equal to efficiency multiplied by theoretical work. Okay. So this is the actual work out. Because for the calculation of efficiency, etc., we need actually actual work. Here all these terms should be actual. All these quantities are actually actual for this cycle, practical cycle, not the theoretical cycle. Okay. So the theoretical part we can determine from the ideal gas conditions and the process equations. Ideal processes, that is isentropic process. But to determine the power, etc., or thermal efficiency or the work ratio, etc., we need to know the actual quantities. So these are actual quantities and they can be determined from the isentropic efficiency. Okay. In the same way, for the compressor, we can write the enthalpy drop across the compressor multiplied by the mass flow rate. So that is m dot. What is the compressor? Compressor here is CPC for the compressor multiplied by delta T across the compressor. That is m dot multiplied by CPC multiplied by delta T. What is the delta T? Delta T is T2s minus T1. T2s minus T1. In the same way as earlier, we can write the actual compressor work input. So actual. Now we know that this is basically actual compressor work is equal to theoretical divided by this. So it will be the actual. So it will go there and this will come here. So it will be theoretical divided by the efficiency. Okay. So this is the work. Now, here you see that out of these quantities, what we know, the mass flow rate we know, the quantity that is Cp quantities are known, the isentropic efficiencies are known, the temperature T1 is known, the temperature T3 is known. Only thing that T4 and T2 are not known. So, therefore, our target will be next to calculate these two temperatures, that is T2 and T4 from the known quantities that are given. So here only T1 and T1 and T3 and other properties, other thermophysical properties like gamma, Cp, etc. are known. T2s and T4s are to be determined. Okay, that is now the target. Okay, now the pressure ratio between 1 and 2 is given. So P2 by P1 is given as 6 by 1. Again, from the isentropic process, we know that T2s are basically T2. T2 and T28s are same. So basically T2 divided by T1. From the isentropic process, you have already used many a times. That is why I'm not writing it here, or I'm not deriving that. So it is equal to gamma minus 1 by gamma. That is from the isentropic process. For isentropic processes of an ideal gas. Therefore, what is T2s is equal to T1 multiplied by, here it is Rp basically, P2 by P Rp. So Rp to the power gamma minus 1 by gamma. So what is T1? 288, I'm sorry, 283. I'm sorry, 288, it was 288.15 multiplied by 6 to the power gamma for the compression. How much it was given? Gamma for the compression, you see, gamma for the compression, this is 1.4. So it is 1.4. So therefore it will be 6 to the power 1.4 minus 1, that is 0.4 divided by 1.4. So if you calculate, then it will come to be 480.78 Kelvin. I have already calculated that and showing it. Now you must check it always. So therefore, T2s, to avoid time, that is for calculate, to skip the calculation time, I had already calculated it. You should calculate it again. So we have determined it. Next, in the same way, we can calculate, as we know that pressure ratios are same. So P2 by P3 is same as P3 by P4. So we can write T3 by T4s is equal to P3 by P4 whole to the power gamma minus 1 by gamma. Okay. Now this gamma is different. This is for expansion, and that was given. That gamma for the expansion that is in the turbine. So that is given as 1.33 for the expansion. So during this process 3 to 4, it is 1.33. Earlier it was 1.44 for the compression. Now we will use that. And T3 is also known. So what is T4S? Therefore, T4S is equal to, now P3 by P4 is same as P2 by P1 as we have seen. So the same pressure, they are same pressure. So that is Rp to the power. This is Rp. So it will be basically T3 divided by Rp to the power 0.33 divided by 1.33 because gamma is 1.33 for expansion. Okay. So here T4 comes. What is T3? T3 is basically 883.15. That was given. This is 883.15. The temperature is given. So you can calculate it quickly. So that is T4S comes out to be 566.19. Kelvin. All these quantities are calculated in Kelvin so that we can easily put them in the proper formula. T4S is not. Therefore, you see that here T4, T2S and T4S are known. Therefore, we can easily now calculate it. So for the turbine, that is therefore using this equation, turbine actual work WT actual that is efficiency. Now I'm just directly putting that values. So efficiency is given turbine for the turbine efficiency is given as 0.82 in the problem. So I'm directly writing it here. 0.82 into mass flow rate is 16 multiplied by Cp value for the expansion that is 1.11 multiplied by change in temperature that is T3 883.15 minus T4S that is 566.19. If we calculate that, it will come to be 4615.95 kilowatt. Why it is kilowatt? You see that this is mass flow rate, kg per second, multiplied by here. You see that the proper unit you have to follow. Here it is kilojoule per kg Kelvin. So kilojoule multiplied by kg per second. So kilojoule per kg, that kg part it will cancel with the mass flow rate kg, and per second here it will be kilojoule per second, and here it is, that is change in temperature. So Kelvin, and that Kelvin unit will cancel. So it will be basically kilojoule per second, and therefore it will be kilowatt. So you have to follow that. What is the unit of this? This is kilojoule per kg Kelvin. What is the unit of that? Kelvin. So that Kelvin and this Kelvin will cancel. And here it is kg per second. So this kg and this kg will cancel. So finally, this kg will cancel, this Kelvin will cancel, and therefore it will remain as kilojoule per second. So kilojoule per second means kilowatt. So this is basically the uh, turbine work, actual work output. Now for the compressor, in the same way, compressor actual work. What is that? Now it is, you see that the isentropic work divided by the efficiency. So isentropic m dot 16 multiplied by Cp. Cp is 1.008 for the compressor, and this is T2S. So here it will be basically m dot means 16 multiplied by Cp means 1.005 multiplied by T2S. T2S is how much? 480.78. 480.78 minus T1 to 288.15 divided by 0.80. So it should be coming to be this is equal to P P097.49 divided by 0.80, that is equal to 3871.97, 0.86 kilowatt. And here in this part only, that is the theoretical work from the turbine. This is equal to 5629. These are written only for the reference. Okay. Next, therefore, now we can write the ones, or we can calculate the ones which are required for the solution. So the power output of the plant that is net power output is equal to W T actual, this is actual basically, minus W dot C actual. So we have calculated both here, this one and this one. So let us highlight them. WT actual is equal to 4615.95 kilowatt, and WC actual is equal to 3871.86 kilowatt. So this is basically this one, and this one. Therefore we can write this is equal to this minus this. So 4615.95 minus 3871.86 kilowatt. Therefore, W net is equal to 744.09. So this is one of our solution. Next is thermal efficiency. Thermal efficiency of the plant. So what is that? Thermal efficiency is equal to W This is W net actual actually. So W dot net actual divided by Q in actual. Okay, now what is Q in actual? W net actual we have already determined. W net actual we have already determined. Now let us see what is this Q in actual. So Q in actual means heat input in the actual cycle. So what is that? Actual cycle heat input, this one. This this is the heat input. So 2A to 3, that is the heat input. So from 2A to 3. So Q in actual is equal to m dot into delta H. Delta H, because always change in enthalpy for these steady flow processes, the energy that is heat input is equal to change in enthalpy. So for all these, because other quantities are nullified in the first law, so the enthalpy remains. So always you will refer to the first law for the steady flow devices for these equations, and you will get it. That is different from the calculation related to the air standard Otto cycles or diesel cycle or dual cycle. For that, the systems are basically always closed system. Here, these are basically steady flow devices. So these are basically having change in enthalpy as the work or heat transfer, like that. Okay, just like steam power plants. Here, these are all steady flow devices, and the corresponding work or heat, that means energy interactions, are related to enthalpy change. So whether it is constant pressure process or not, that does not matter. That will be change in enthalpy that comes from the first one. Okay, so there is m dot Cp for this heat input process, Cp for the combustion. This is called combustion, multiplied by change in temperature, that is T3 minus T2 actual. Okay, now we do not know yet what is T2 actual. We have determined all the T2 isentropic here. Although we have determined T2 isentropic, let us see this one. Okay, we have determined it, but T2 actual is not known. So that will be determined from this relation. Here you see that from this relation we will determine the T2 actual, because T1 is known, T2 ideal or the isentropic is known, and this is known. So we can determine T2A from this relation. We will use that relation here to determine T2 actual. From that equation, I think equation 2, from equation 2 is equal to T2S minus T1 divided by T2A minus T1. So T2S is equal to, so it means basically this is equal to 0.80 is equal to, what is T2S? Just determine 480.78 minus 288.15 divided by T2A minus 288.15. From this, we can determine what is T2A. T2A is equal to 480.78 minus 288.15 by 0.8 plus 288.15. Just rearranging the above equation, we will get it. And here we get T2A is equal to 528.94 Kelvin. Okay, T2A we have got, therefore here T3 is known, T2A is known, and other quantities are known, therefore we can determine what is Q. So therefore Q in actual is equal to mass flow rate 16 multiplied by A, that is Cp for combustion, how much it is given? That is 1.11. 1.11 multiplied by T3. T3 is the maximum temperature, that is 883.15 minus, just determine 528.94. So therefore it comes to be Q in actual is coming to be 6290.77 kilowatt. Therefore, this is this. Okay. Therefore, the thermal efficiency is W net by Q in. So that is eta is equal to 744.09 divided by 6290.77. That means basically is equal to 0.1183. We see that the thermal efficiency is about 12%, that is 11.83%, or is equal to 11.83%. It is very less, although that is one disadvantage of a gas turbine system where the compressor work is a substantial amount from the turbine work output. So you see the turbine work output is this one, but the compressor work output is almost most of the part of that. Okay. So now we will see the work ratio, and from that we will get that idea. Next quantity that we will determine is, so here it is, this one. Efficiency is 11.83%. Next quantity is work ratio. That we will denote with R work is equal to W dot net divided by W dot T, that is turbine. So it is W dot net. What is that? W dot net is 744.09 divided by 4615.95. So this is about 0.1612. That means what? Out of the turbine, total turbine work output, this is the net realized or realizable work output. This is the total turbine output, total turbine work output, and this is the realizable work output. Okay. So that we see that this is the ratio of the net work output to the turbine work output, and therefore we see that only 16% of the total turbine work output is realizable work output, and the remaining 83.88%, that is 16.12%, 100%, 100 minus 16.12, that is about 83.88% is consumed by the compressor. So that is one observation additionally. Next, this is up to the end of the problem. So according to the requirement of the solution of the problem, this much is needed. Now, additionally, we may determine the theoretical efficiency or theoretical air standard efficiency for this plant. So if we want to do that, then it is additionally done. So the reversible or the ideal cycle thermal efficiency, if we want to determine. If we want to determine. Now, what we will see that in case of ideal air standard cycle or the air standard cycle, that is Brayton cycle, there is a constant property assumption. But here you see that in the problem, all the variations, all the CP variable, CP variations are given. That means for different processes, these are different. So accordingly, we will take that for calculation of the idealized version of this cycle. So accordingly, what will be the thermal efficiency? Let us see. So what is that? Basically, from the definition, it is W dot net divided by Q dot in. Now W dot net, here we will not write in terms of Q in, Q minus W dot net is equal to Q dot in minus Q dot out. We will not write because for the heat rejection, there is no information related to Cp or gamma given. So we will better stick to that compressor work and turbine work in relation to the calculation of W dot net. So it will remain as turbine work and compressor work. So W dot net is equal to basically W dot T. Now it is isentropic minus W dot C isentropic divided by Q dot in. This is theoretical. So therefore it will be therefore mass flow rate may be cancelled because everywhere mass flow rates are same. Now here we will be writing only Cp into delta T. So delta T means basically for turbine it is 3 minus T4s minus Cp. This is for expansion. Expansion, and this is for compression. So Cp into delta T, that is basically T2s minus T1, and Q in basically Cp for the conversion multiplied by T3 minus T2. Yes. Now here I am not writing, you have to follow one thing, that I am not writing the definition, that is for the ideal or the air standard cycle as equal to 1 minus 1 by Rp to the power gamma minus 1 by gamma. I'm not writing because in that there was an assumption, or there were assumptions, that is CPs are constant. There was the assumptions, right? CPs are constant and gamma constant. So these were assumed. Therefore, all the other quantities like Cp, etc. were cancelled. And it came in terms of R to the power Rp to the power gamma minus 1 by gamma. But here, since the Cp values are different, they will not cancel, and therefore we have to calculate separately. That is the difference that you have to keep in mind. You cannot directly calculate. Okay. So here it will be simply if we just put the values, because all the values we have determined just, so you can put the values 1.11 for the expansion. T3, what is that? T3 is equal to 883.15 minus T4s. T4s we have not yet determined, I think. T4s. So T4s we have to determine. T4s we have not yet determined. Now Cp compression, it is 1.005. T2s is equal to 480.78 minus 288.15 divided by Cp. For combustion, it is 1.11 multiplied by T3. T3 is 883.15 minus 480.78. Therefore, to determine the air standard efficiency, we have to determine this quantity. This quantity we have not yet determined. Now, how to determine that? In the same way that we have determined the this quantity. In the same way, T2s. Sorry, in the way that we actually calculated 4s, right? So what we have to determine 4s. 4s, I think we have already determined. So 4s is already determined. So yes, 4s is determined. So it is 566.19. 566.16. We have already determined that. Now we can put it here, 566. Therefore, so it is 5 5 566.19. Therefore, it is coming to be let us do it. So that comes out to be 0.3542, or the air standard efficiency for this is 35.42%. You see that for the actual cycle, it is about 11.83% or about 12%, and for the no loss that is frictionless compression and expansion, this is about 35%. So due to that friction, although the heat Q, that is Q in is also increased, that means in the ideal process Q in is more, but the net work output is much more compared to the increase in heat in. Therefore, effectively, the thermal efficiency increases. You can individually calculate this quantity, what is happening here. So you see that this is about the numerator, that is net work in per unit mass is about 158.23, and the net heat in per unit mass is about 446.63. So per unit mass means basically kilojoule per kg. This is in kilojoule per kg. You see that this is this and this is this. And in case of the ideal one, per unit mass, if you divide both by 16, you will get about, this will be about per unit mass, this will be about 46, about 46, roughly 46 kilojoule per kg. And this is roughly about 393. 1 point. You see the difference. Here it is 46 per 393. So in the ideal, this is also increased. You see, the heat in is increased because the process is here from 2A to 3 instead of 2S. So this amount of heat supply is saved, but the work is lost. There is a loss in work, and that is, you see, this is in the ideal case, this is 158. And in the theoretical case, it is 46. So both are increased in case of ideal, but the work is increased much more compared to the heat addition. So from 393, it is increased to 446. But here it is almost, it is more than 3 times. The work is increased more than 3 times. So that is why the efficiency is increased about 30. This is the ideal case. So it is about 35%. Another quantity that additionally we can calculate, another quantity that we can additionally calculate here is the actual turbine exit temperature So in the same way that we have calculated the actual compressor exit temperature. So here you see that we have calculated the compressor temperature, exit temperature, this one, compressor exit temperature. So using the efficiency, isentropic efficiency, we will also determine the turbine exit temperature using the turbine isentropic efficiency, this equation, equation 3. So we will use that. So we know that turbine isentropic efficiency is equal to H3 minus H4A divided by H3 minus H4S. Therefore, it is equal to T3 minus T4A divided by T3 minus T4S. So we know all things except this one here. Except this quantity, we know everything else. I'm sorry. Very sorry. Except this quantity, we know everything else. Therefore, we can determine this in this equation, from this equation. So this is basically 883.15 minus T4A divided by 883.15 minus, this is 566.19. So here you can solve this. Therefore, T4A is equal to 883.15 minus 0.82. This is 0.82. This is 0.82. Therefore, multiplied by 883.15 minus 566.19. The unit should be Kelvin. So after just calculating, it comes to be 623.24 Kelvin. So 4A. Therefore, it is this. So these are the additional things that we have determined. Now just put the values of temperature there so that we can clearly understand what is there. Just put the values of the temperatures exactly so that we can understand. Let us put them. Here it is. T1 is how much? T1 288.15. T2S. What is the temperature? 480. Let me write it somewhere else. 4 480.78. This is, what is that? 2A. What is that? temperature of 2A. So that is 528.94. And what is T3? T3 is, there is only one value, 883.15. What is 4S? This is 566.19. And what is 4A? This is 600. We have just determined that 623.24. So you can clearly understand this is isentropic. So only reversible work input, due to that 480.78 is the temperature, the final temperature. And due to frictional heat generation, there is higher temperature here at the final state in the irreversible process. Now after that, you see that therefore the heat addition here is saved, because the temperature is 528 instead of 420. Therefore, it's about 50-degree temperature, about 48-degree temperature already increased. Therefore, this amount of temperature rise is saved in the combustion process. And here the temperature is only one, that is 883.15. And in the case of isentropic process in the turbine, it is 566 after the full expansion. 566, all these temperatures are Kelvin that you have to write. All are in Kelvin. And in case of frictional, that is heat generation. Heat generation is there, but there is no way of heat rejection or heat, that means heat supply or heat rejection to the surroundings due to the adiabatic process. So there is extra temperature in the turbine exit, that is 623. So it's about more than, it's about I think more than 50 degrees centigrade. Yes, it's about 34 and 23, means it's about 57 degrees centigrade extra temperature in the turbine exit. So this is quite understandable. So this is the problem, and I'm stopping the lecture today. So these type of problems can be solved, and also some more insights can be derived from this type of problems. So this is a sample problem, and this is one illustrative problem where I tried to explain all the relevant details related to the problem. Not only I solved the problem, I tried to explain the relevant physics or engineering related to the solution. Thank you.